This is Electromagnetic Motor Lab Report number 2 by Beth, Sarah, and Caitlin.
In this experiment, our group investigated magnetic force derived from a battery-powered circuit. The main goal of our investigation was to increase the speed of rotation of a wire loop by increasing the magnetic force. The magnetic force was strengthened by increasing the number of magnets and increasing the voltage, independently of each other. The main goal of this experiment was to be able to understand the relationship between current, the magnetic field, and the speed of rotation. After analyzing our data, we concluded that increasing the number of magnets and batteries, both independently, increased the speed of rotation of the wire loop. Additionally, our setup is diagrammed on this slide. We stabilized the wire loop by resting it on 2 copper wires rested in Play-Doh, which were connected to a battery power source via alligator clips and wires. Magnets were then placed directly underneath the wire loop. To be able to track the velocity of the wire loop, the tracker program was utilized.
As we know, currents create an electric field and magnets create a magnetic field. With both fields flowing together, they are able to create and impose a force on an object. For this experiment, in order to allow the created currents to flow through the circuit, the wire must be stripped. We hypothesized that increasing the number of magnets will increase the strength of the magnetic field, therefore causing the coil to spin faster. We also hypothesized that increasing the number of batteries will increase the strength of the electric field, therefore also causing the coil to spin faster.
This experiment used a small, understandable model for real-world large electric motors. First, we noted that as we attach the setup to batteries, the circuit will become complete and current will flow through. Then we looked at the fact that magnets create a magnetic field as shown in the image. If we combine these factors together, we find a connection between these 2 variables called the Lorentz force equation. This basically states that if there is a moving current along the magnetic field, there can be an overall net force created. It is also important to note that the force, current, and magnetic field vectors are all perpendicular to each other, so we can determine the direction of the vectors using the nifty trick of the right-hand rule. We also included dimensional keys of a circle with an X, which tells us the vector is going into the screen, and a circle with a filled circle indicating a vector is pointing out of the screen. As you can see, we broke down the scary, complicated electric motor into simpler, easy models, which assist us in comprehending how and why the motor works. In a perfect world, we would hope that as you increase the voltage or you increase the number of magnets, the velocity of the coil will increase proportionally.
We found that increasing the number of magnets did in fact cause the coil to spin faster, as with more magnets, the velocity of the coil increased. With 8 magnets, the velocity was 4.5 centimeters per second. With 10 magnets, the velocity jumped to 5.05 centimeters per second. And with 12 magnets, the velocity of the coil increased to 6.9 centimeters per second. We also found that increasing the voltage of batteries also caused the coil to spin faster. This can again be seen by an increase in velocity of the coil. With a battery voltage of 1.5 volts, the velocity of the coil was 3.06 centimeters per second. With a battery voltage of 3 volts, the velocity of the coil was 6.98 centimeters per second. And with a voltage of 4.5 volts, the velocity jumped all the way to 11.32 centimeters per second.
Our results actually correlated pretty well with the ideal results. We are able to conclude that by combining magnets with current, an overall force is established in which causes the coil to spin. In both experiments, the velocity, and therefore the force, increases approximately linearly. We also discovered that if we didn't strip the wire in the proper way, the current would not work. This is due to the fact that with no stripping, the current would not be able to travel through the copper bars across the coils and into the other copper bar. With no current flowing, the coil cannot spin because there is no force. We know this is due to the Lorentz force equation, which states the current and magnetic field are required to create a force. Therefore, if the current is 0, the resulting force will also be 0. The reason one side of the coil needed to be stripped was to create an overall net force in which makes the coil to spin. If the whole thing is stripped, the net force will actually equal out and not cause the coil to spin. By leaving a side unstripped, we change the overall net force on the coil, which causes it to spin. We actually determined all of this using the right-hand rule.
Our group hypothesized a few methods in order to increase the effectiveness of this experiment. One way would be to change the metal used to a more conductive metal rather than copper. Additionally, changing the material of the wire loop to be more conductive would also increase effectiveness. Thirdly, having stronger magnets would allow a stronger magnetic field to be created, therefore increasing speed of rotation. Likewise, changing the length of the copper wires in order to account for a larger amount of magnets underneath would also increase the speed of rotation. Lastly, using a tachometer to measure speed of rotation rather than a program like Tracker would also increase the accuracy of the experiment.
That's all, folks.